Hello everyone, my name is Amir Dorudian.
And I'm Cooper Clinton.
Today we're going to be talking about closed-loop control systems and UAVs, and we're mostly going to be talking about ArduPilot and flight controllers.
All right, so first off, just a quick introduction. A closed-loop system is a system with continuous feedback. It's essential for autonomous drone flight. And our focus today will be on the Pixhawk hardware and how the ArduPilot software runs that and how it uses the sensors, actuators, and controller shown in the loop below to operate the drone and to make autonomous flight possible.
Basically, a closed-loop control system is one that compares the actual output data to our desired input data, and our sensors are able to measure the performance of the UAV all in real time and send that data to the flight controller, which figures out an error. And once an error is calculated, then we can send commands to the actuator to carry out various corrections, and this cycle runs continuously all the way up until the flight is over.
Now I'm going to go into a little bit more about why UAVs actually need closed-loop control systems. So drones in the perfect world would be able to fly directly to a waypoint set for them, but in the real world they'll face wind, turbulence, and shifting payloads. So with that closed-loop system, it'll be able to correct for these minor issues. Also with a closed-loop system, it allows for steady hover as well as aiding in navigation. And finally, the closed-loop control system will enable both assisted manual piloting as well as full autonomy.
So yeah, you may be wondering, what is the difference between Pixhawk and ArduPilot? Well, it's as simple as this. Pixhawk is the hardware, it's the physical chip, while ArduPilot is the software that runs on the chip. And ultimately together they're able to plan out and execute an entire flight plan.
Now I'm going to get into the controlled operations in a UAV. First we have attitude, which is going to be your roll, pitch, and yaw stabilization. Then we have altitude, which will maintain the set height. Next we have position, so the drone will know the position that it is going to, and based on its current position know how to get there. That also measures velocity in 3 directions. And all these systems rely on nested feedback loops, and so kind of like I was saying before, it will get live data, continuously read it, and then make corrections for that.
So once our flight controller gets a % error, then it sends commands to our actuators. And 2 examples of actuators would be our servo motors and our propeller. Our propeller is what's connected to the AC motor, which ultimately controls the thrust of the aircraft, while the servo motor is what controls how we turn either left, right, go up, or down.
So here we have the sensors, which is going to act as the drone's eyes and ears. It'll be the input data so the drone knows what's going on around itself. The IMU is comprised of the gyroscope and accelerometer for orientation and motion. The GPS provides global position as well as velocity. The barometer will indicate altitude using air pressure, and the magnetometer will tell the drone its current heading. The feedback loops depends on how fast these sensors will update. Most of this is built into the Pixhawk flight controller, except for the GPS, which you can see in the bottom right there.
So yeah, ultimately inputs define what the UAV should do. They can either come from the pilot using stick commands, or it can come from the mission planner, ArduPilot. And either can go into autonomous mode with waypoints, kind of how we'll show later on, or with what that image shows on the bottom right, or the pilot themselves can control it, kind of like how you were to play a video game.
So here we have the outputs of the UAV. So outputs are what the drone is doing in real time. So some of the examples of this are the actual speed of the propeller, the actual angle of the different control surfaces, the maintained altitude, how much it's drifted, and where the GPS is saying we are versus where we need to be.
So ultimately, with this control loop, basically we can go all the way from our desired output to the actual output. And our controller would be the Pixhawk, the actuators would be the servo and the AC motor, and the process would be the whole drone itself. And some sensors would be like the barometer and the GPS.
Some possible improvements that we could make to UAV control in general would be obstacle detection and avoidance using LiDAR, radar, or AI vision. So this would be able to detect objects in the real world and move to avoid them instead of relying on previous data. Along with this, we have adaptive AI controllers that would be able to tune themselves, just kind of taking out a step for whoever's kind of managing these drones. And then as well, we'd have smarter energy management, so making the drones more efficient overall and potentially reducing the number of components again, to save energy and to increase flight times.
So yeah, in summary, our UAVs that have Pixhawk hardware and ArduPilot software are an excellent example of the control loop control systems. And again, our sensors detect the errors, sends that data to the flight controller, which is able to figure out what movements need to be done. That data is then sent to the actuators, which actually moves the aircraft. Ultimately, all of this ensures that we have a good, reliable, autonomous flight.
Finally, we have some review questions. So number one, we have, what actuator provides thrust to the UAV? The answer would be the motor. And the second question, what is the process being controlled? And that would, of course, be the UAV itself.
Here's kind of our part 2 of the video where we're talking about the ArduPilot software. As you can see on the right-hand side, we have our GPS info where you can see we're in a no-fly zone based off our location. And then on the left-hand side, we have all of our inputs like our altitude, ground speed, and many more. And then we also have kind of our, at what degree is the aircraft? Are we turning? Are we going upwards? Are we going down? Are we upside down? So we're able to see kind of our pitch and yaw based off of that. And then we're also able to, using the software, as we said, plan autonomous flights. So from my house, we can kind of set waypoints and go basically from my house to point A, to point B, to point C, to point D, back to point A, and we're able to set our altitude. So here we're at 100 feet, 100 feet, 100 feet, 100 feet. And from there, we're able to move it on to the simulation where we're going to say, hey, we're using a plane with all of these specs, help us make this mission. And yeah, ultimately, that's kind of what someone like myself, if I were to be flying right now, would see as a UAV pilot. And then the second part, we're going to be showing off the components of an aircraft itself. And here's a fixed UAV or fixed wing drone that I've brought in. We have many, many parts, and the main part that I want to talk about is the flight controller right up in the center. The flight controller, again, is what has all of our inputs and is the main communicator between our ground station, like our ArduPilot software, versus the actual hardware, which is our control system, or our flight controller. Flight controller also connects to an ESC and a motor, which is what controls our thrust. It also controls, the flight controller is also connected to 2 servos, which controls kind of our flaps' degree of attack, or angle of attack. And then it also has the GPS, which we've talked about many times. It's the GPS is one of the only input sensors that is not included within the Pixhawk itself, which is our flight controller. We also have an area for our battery and a camera system, all that connect back to the flight controller. So again, the flight controller is kind of like brains, while everything else is like the arms and the legs that moves our body. So yeah, thank you guys for watching, and hopefully you guys have learned a little bit more about fixed UAVs.